Today in Math 30-1, we're looking at the last topic, 9.3, connecting graphs and rational equations. The roots of rational equations are going to be the x-intercepts of the graphs of rational functions. That's going to be if we set them equal to 0. The algebraic solution to the equation 8 over x squared minus 16 plus 1 equals 1 over x minus 4 results in x equals negative 3 and x equals 4. We're just giving you those for now. Later on in this lesson we'll show you how to find those. Well, however, x equals 4 is called an extraneous root because in our original equation x cannot equal positive 4 or negative 4. And since x equals negative 4 is supposed to be a potential solution, we have to throw it out. If we graph our equation, the graph shows the only one true solution at x equals negative 3. Here's what it looks like. Notice that there is only one x-intercept because if we brought this equation all over to one side, where we got an f of x is equal to 8 over x squared minus 16 plus 1 minus 1 over x minus 4, that's going to be our solution of x is negative 3. We can also notice that the graph will not, I repeat, not show you the extraneous root. It only comes up when we solve our graph algebraically. In example 1, we're going to relate the roots and x-intercepts. A. Determine the roots of the rational equation algebraically, and then graph the rational function and determine the x-intercepts. And what's the connection between the roots of the equation and the x-intercepts of the graph of the function? Well, here's A. First of all, what we're going to have to do is we're going to have to multiply both sides of our equation by the common denominator. That's going to get rid of our denominators. The common denominator in this case is our only denominator of x plus 2. So what you're going to do is you're going to multiply every term on both sides of the equation by x plus 2. That gives us x times x plus 2, as shown here, plus 6 over x plus 2 times x plus 2 equals 5 times x plus 2, and that's going to equal 0 times x plus 2. Now, since everything is multiplied by x plus 2, we can cancel the x plus 2 on the top and the x plus 2 on the bottom of our second term. So that's going to give us x times x plus 2 plus 6. Those two cancel out. Minus 5 times x plus 2, and that's going to equal 0. To continue and clean this up, you're simply going to move things around until you get x squared minus 3x minus 4 is equal to 0. Now we can factor that into x minus 4 times x plus 1 means that there's two possible roots, x is equal to 4 or x equals negative 1. Since our non-permissible value is at x is negative 2, both of these solutions are acceptable. You can check algebraically or you can check by graphing. Notice that in this case, if we took our function to be x plus 6 over x plus 2 minus 5, we're going to get two x-intercepts. One of our solutions is going to be at 4, 0, so x equals 4, and the other one is going to be at negative 1, 0, so the other solution is x is equal to negative 1. In example 2, we're going to examine approximate solutions for rational equations. By approximate means that they're only asking us to get it to the nearest hundredth, thousandth, tenth, whatever. So these are going to be decimal approximations. When we're solving a rational function, like rational equation, like x squared minus 3x minus 7 over 3 minus 2x is equal to x minus 1, there's a couple different ways we could do it. In our first one is A, we could make x squared minus 3x minus 7 over 3 minus 2x, and then we can subtract x from both sides and add 1 to both sides. And as you can see, we've got, this is what we have here. And then on the second thing we can do is make y2 equals 0 and then find your x-intercepts. Pardon me, your x-intercepts using the calc function on your calculator. As you can see, there's going to be two x-intercepts, one at 3.097, one at negative 0.4305. Those are the two roots of our equation. The second way you could do this is you could just make y1 equal to the left side of the equation, and you can make y2 equals the right side of your equation, and then find the intersection points using the same method. Both ways, you're going to get x is equal to negative 0.4 and x is about 3.1. Okay, now we have to verify it algebraically. We take our equation, x squared minus 3x minus 7 over 3 minus 2x is equal to x minus 1. Again, to solve a rational equation means you have to multiply both sides of your equation by your common denominator. Here it's 3 minus 2x. So if I multiply the right side by 3 minus 2x and the left side by 3 minus 2x, notice on the left side I can cancel the 3 minus 2x's. I'm left with x squared minus 3x minus 7 is equal to x minus 1 times 3 minus 2x, which is going to give me x squared minus 3x minus 7 is equal to 3x minus 2x squared minus 3 plus 2x. Cleaning all this up, bringing everything over to one side of our equation, means I'm going to get 3x squared minus 8x minus 4 is equal to 0. Since this is not factorable, I'm going to use my quadratic equation and figure out that 8 plus or minus the square root of 112 divided by 6, it gives me two roots. I'm not going to worry about reducing this for an exact answer. I'm just going to take 8 minus root 112 divided by 6 to get negative 0.4305, and 8 plus root 112 over 6 to get 3.097. Now, the algebraic solution is going to give me exact solutions, but in this case, we're just going to round them off because this is all we're looking for. In example 3 now, we're asked to solve this equation algebraically and graphically, and compare the solutions found using each method. In A, we're going to take x over 2x plus 5 plus 2x is equal to 8x plus 15 over 2 times 2x plus 5 if I factor the 4x plus 10. Notice my non-permissible value is that x cannot equal negative 5 over 2. And the first thing I have to do is multiply both sides by my lowest common denominator, which is 2 times 2x plus 5. So, writing this out so I have a little bit more room, I'm going to start by saying the first term times 2 times 2x plus 5, the second term times 2 times 2x plus 5, and our third term times 2 times 2x plus 5. Again, in the first term, we're going to cancel our denominators, 2x plus 5, with a 2x plus 5 from the top. Means my first term is going to be changed just to 2 times x. Now I'm going to have 2x times 2, which is 4x times 2x plus 5. And on the last part, both 2 and 2x plus 5 are going to cancel on the bottom with the 2 times 2x plus 5 on the top, leaving me with 8x plus 15. Now I can clean it up and bring everything over to one side, and I'm going to be left with 8x squared plus 14x minus 15 equals 0. Now on this one, I can use decomp. But if you can't find that, what you can do is just use the quadratic equation. That always works. And you're going to get two roots. X is going to equal negative 5 over 2, or x is equal to positive 3 over 4. 3 over 4 I can circle, and negative 5 over 2 I'm going to circle, but when I check my non-permissible values, we said in the beginning that x could not equal negative 5 over 2, so I'm going to cross that out. And when we graph our solution, you're going to see that there's one intersection point, and that's when x is equal to 0.75 or 3/4. In example 4, we're going to solve a problem. In basketball, a player's free throw percentage is given by dividing the total number of successful free throws by the total number of attempts. So far this year, Larry has attempted 19 free throws and has been successful on 12 of them. If he is successful on every attempt from now on, how many more free throws does he need to attempt before his free throw percentage is 80%? Well, we're going to let x equal the number of free throws that Larry takes from now on. P is the probability of success divided by attempts. So we're going to say 12 out of 19, but we're going to add x to the 12 and x to the 19. And we're going to substitute P with 0.8. So 0.8 is going to equal 12 plus x over 9 plus x. 19 plus x, I'm sorry. When I multiply both sides by 19 plus x, I'm going to be left with 0.8 times 19 plus x is equal to 12 plus x. And simplifying this equation gives me a value of x is equal to 16. Larry will have an 80% free throw percentage if he makes the next 16 in a row. Graphically, if we look at it, you're going to see that it's going to intercept at y is equal to 16, at y is equal to 0.8, I'm sorry, when x is equal to 16, y is going to equal 0.8. In summary then, you can solve rational equations both algebraically or graphically. The solutions or roots of a rational equation are the same as the x-intercepts of the graph of the corresponding rational function, and you can use either of the methods for solving rational equations. You can manipulate the equation so that one side is equal to 0, and then find your x-intercepts, or you can graph a system of functions where y1 is equal to the left side, y2 is equal to the right side, and find your intersection points. When solving rational equations algebraically, remember to check for extraneous roots and to verify that the solution doesn't include any non-permissible values. Your assignment then is to do page 465, numbers 1 to 9.